Morning, everyone. The rapid increase in small unmanned aerial systems has created a serious gap in our existing detection infrastructure. Standard visible light cameras fail in low light and foggy conditions, and that is where infrared thermal imaging fills the gap. But it also comes with its own challenges. These drones appear as tiny, low contrast pixel clusters in the image, and detecting them reliably in real time on embedded hardware is genuinely hard. Today's presentation walks through how that problem is tackled using deep learning and optimization to push detection performance further. The foundation of this work is a man-portable computer vision system developed at the UT Arlington Research Institute, designed to detect drones and vehicles in infrared imagery. The prior system was functional, but it had a key limitation. Hyperparameter tuning was never performed, and the model was essentially operating on default settings, which capped its performance. This work addresses that gap using a two-stage tuning strategy: a genetic algorithm for training time parameters, followed by a grid search for testing time parameters. The result was a measurable improvement in performance, with MAP 50-95 increasing from 0.54 to 0.59, nearly a 10% gain over the prior system. The dataset used in this work is a custom infrared drone dataset developed at Utari, and it presents a genuinely difficult challenge. The imagery suffers from low contrast and significant variation in scale depending upon the drone's distance, and the complex backgrounds make the targets easy to miss. To ensure that the model generalizes well, standard data augmentation techniques were applied along with a proper testing a train and test split. After evaluating several architectures, the experiments converged on YOLO V12, which was tested on both a desktop GPU and an embedded GPU to validate real-world deployment feasibility. The tuning strategy here is intentionally two-stage, and that design choice is important because the first stage uses a genetic algorithm which efficiently explores a large hyperparameter space by evolving candidate solutions over multiple generations. Rather than exhaustively testing every combination, it naturally converges towards high-performing regions of the search space. Once the optimal training configurations have been identified, the second stage applies a grid search to the testing time parameters. Grid search is exhaustive and methodical, making it ideal once the parameter space has been narrowed. Together, these approaches complement each other effectively. Mainly here, three training time hyperparameters were targeted. Learning rate determines how large each step is during training. Too large and the model overshoots, and too small and the learning becomes slow. Momentum helps stabilize training by accumulating past gradients, which is especially useful in uneven loss landscapes, where the key acts as a regulator, preventing the model from overfitting by discouraging excessively large weights. All configurations were evaluated using a single scalar metric called fitness, a weighted combination of MAP at 0.5 and MAP across the stricter 0.5 to 0.95 range, with greater emphasis on the stricter metric. The second stage focuses on optimizing testing time parameters, confidence threshold, and intersection over union threshold. A detection is only considered valid if the model's confidence exceeds the first threshold and the predicted bounding box sufficiently overlaps the ground truth according to the second. These thresholds play a critical role in real-world reliability. The full tuning process requires approximately 16 hours on a dual RTX 5090 system and a meaningful computational investment, which is a meaningful computational investment that resulted in consistent and reproducible accuracy improvements. Um, Here, the results. The original baseline achieved is at an MAP 50-95 of 0.54. And after applying the genetic algorithm for the training time hyperparameters, or the performance increased to 0.55. And finally, after incorporating the grid search for testing time parameters, the score was raised to an value of 0.5906, which is approximately a 10% improvement. Now let's look at the parameters to learn more about them. A lower to medium learning rates combined with medium to high momentum consistently produced better results. Weight decay values in the lower to medium range also improved performance. At inference time, the lower confidence thresholds led to higher MAP 50-95, suggesting that allowing more candidate detections improves overall accuracy. Interestingly, the IOU threshold did not show a significant impact within the tested range. In conclusion, this work demonstrates that hyperparameter tuning is not optional for high-performance detection systems, it is essential. A nearly 10% improvement was achieved without modifying the model architecture or dataset. Looking looking forward, further tuning could yield additional gains, and next steps could also include enabling deployment on embedded systems through post-quantization training, particularly targeting hardware such as NVIDIA Jetson to achieve real-time edge deployment. Finally, I would like to thank Dr. Suhas Shalian at Utari for advising this work and CSERE program for the support. The prior research was conducted by a graduate student named Joshi Jiruta, who provided all of the foundation that made this work possible. Thank you.